We'll give it just a few more minutes if anybody else shows.
Okay.
Well, it's 10 o'clock. We get some more people, we get some more people. If not, we don't. So that's okay. No agenda? Ask questions. What you got for me?
I think the thing that I struggle with the most is the Newman projections.
The Newman projections?
Because I've never been good at like models and like seeing like STEM basically, so I don't really know how to like, I don't know, like, I think it might, I don't know if it confuses me with doing it with the models or if I'm not doing it right,
Okay.
but I
You
just
got
don't
your model
really-
kit with you, right?
Yes. I
So
just don't know like where to start. I know that like the like staggered and then well, I guess eclipse like
Yeah.
are on the sides,
Okay.
but I just don't really know. Like in a test question, I don't think
Okay.
I would be good at doing it.
Let's take butane as an example. Right? So when we're thinking about Newman projections, we're always going to be looking down a carbon-carbon or some kind of bond, right? And so if I had my model built, right, and I have my eyeball here looking, right, I'm going to be looking down what I would call the C2, C3 bond, right? Because carbon 1, carbon 2, carbon 3, carbon 4, right? And so as I build that model, and I look down that C2, C3 bond, this is what I'm going to see. Right? The front carbon is represented by the dot, right? The back carbon, which is carbon number 3, because my eye is here looking at carbon 2, right, is going to be the, excuse me, the circle. And what I see looking down this carbon 2, carbon 3 bond is I see a CH3 that's going to be pointing straight down. And then this carbon has 2 hydrogens on it. Right? And this carbon number 1 and carbon number 4 are as far apart as possible. They're 180 degrees to one another looking down this bond. So that means that the other CH3, this one, carbon number 4, is up. And these 2 hydrogens are down. So, let me see your model kit. So what we're going to do Remember when we're putting together our model kit, we take 2 of the black pieces and we have to snap them together. It'd be a good idea to have these already snapped together before you come into the exam on Tuesday. And we need 4 of them, which is 8 total pieces that have to be put together. And now we're going to connect these together to make butane. And then what you should see is that what I drew is that model. Can you see that? Okay. And so when I'm looking down this carbon-carbon bond, that means to grab the carbon and look at it like this. So from my perspective, this is the front carbon. This is the back carbon. So this front carbon is the dot. This back carbon is the circle. And what I can see are the 2 hydrogens here. And I can see the methyl group pointing down. And on the back carbon, I see the 2 hydrogens here and the methyl group coming up. So that's the Newman projection, right? That's the Newman projection. And in fact, that's exactly what you would see if you smashed this into a 2-dimensional piece of paper. So essentially what we're doing is we're taking this and we're just shoving it into the board. And that's what's giving us the Newman projection. You don't see this bond because you're looking down it. That's represented by this and this, right? And so this is carbon 1, carbon 2, carbon 3, and carbon 4. That's how that goes. And then as we can rotate, right? And we can look at different Newman projections. Does that help?
Yes.
Okay, good. What else?
A note for me, I was doing chapter 2 problems at the back of the book, like the odd problems, and I was looking at one, and it was like, tell like which sort of equilibrium the reaction will be on, because it gives you acetic acid like a base. And my question is, if they're both a weak acid and a weak base, then why would the equilibrium necessarily be on their side?
Okay, so give me an example. Give me the example.
It's like one of the problems.
Give me the problem.
It's like a reaction between acetic acid and sodium HCO3. Sodium.
Bicarbonate?
Yes, sir.
Okay, so which one is it?
It's number 25.
Okay, so acetic acid. I'll just draw it out like that. Plus sodium bicarbonate, right?
Right.
What does that give us? That gives us sodium acetate plus H2O plus CO2, which is a gas. All right? Now the question says, okay, this equilibrium lies mostly to the products. What's the pKa of bicarbonate?
Uh, 10.33.
1033. So the pKa of this, let's just call it 10.3. The pKa of acetic acid?
4.76.
4.76. What's the pKa of water?
15.7.
And the pKa of, do they give the pKa of sodium acetate?
No, sir.
Okay, so they don't. But we can think about it, right? So this is the Lewis acid. Will you agree?
Yes, sir.
This is the Lewis base. This is the conjugate base. And this is the conjugate acid, right? I'm going from a stronger acid to a weaker acid. So which way does the equilibrium lie?
You lie to the right.
It'll lie to the right.
Okay.
Yep, so it lies to this side.
Okay. That makes-
Okay, so your equilibrium is always going to lie to the side of the weaker acid,
Right.
weaker base pair. And it turns out that this is a fairly weak base. Now, I know looking at this that the equilibrium is going to lie far to the right because it's also generating carbon dioxide, which bubbles out of the
Right.
reaction mixture. But always look at find the acids, find the bases, determine which one's stronger, which one's weaker. Okay? So that's the way that you would approach such a problem. Let me make sure I'm getting all this into the camera. Get most of it.
Okay, and then my next question is, the EZ system or the cis-trans, whenever you are looking at it in like a fine angle formula, just like go back over like the first steps, like when you see like the alkene and then you are looking at the sides that are cis and trans, just go back over the first steps.
Okay.
And understand like the meaning, like, okay, this is E, this is Z, but I don't really know how to do it.
All right, when we look, first thing you have to do is find the double bond and identify the carbon atoms of both carbon atoms that are part of that double bond, right? Then you got to assign priorities to the groups that are attached. Well, this bond line drawing, when I look at this carbon, it's attached to a carbon and it's attached to a hydrogen. So I'm going to draw it out for clarity. And this one's attached also to a hydrogen. So what we have to do is figure out the priority, right? So I've got hydrogen and I've got carbon. Which one's the higher priority?
Carbon.
Carbon, and that's right. So this is the higher priority, this is the lower priority. Now I look at this carbon, and I do the same thing. It's got a carbon, it's got a hydrogen, so this is low, this is high in terms of priority. Now I just look at the plane of the double bond and I ask myself, where are my high priority groups? Right? High, high are on opposite sides, so this is
E?
This is an E alkene. Or we can also call it
Trans.
a trans alkene. Let me give you something a little different. We're going to do exactly the same thing. Right? We're going to look at this carbon, and we're going to look at this carbon, and we're going to see how things are relative to that plane. So let's just take them one at a time. This carbon of the alkene's attached to a CH3 and a CH2. Both of those are carbons, right? So can I make a decision based on that alone? No, I have to ask myself, what is this carbon attached to? And I always put these in parentheses. It's attached to 3 hydrogens. Right, that's a CH3. What's this carbon attached to?
2 hydrogens.
And
Another CH3.
another carbon, right? So we're going to put them in order here. Now I'm going to look at these. What wins, carbon or hydrogen?
Carbon.
Carbon. So this is going to be the high priority group. This is going to be the low priority group. Let's do the same thing here. I've got a carbon in both cases, right? This carbon again is attached to 3 hydrogens. And this carbon is attached to what?
Another carbon.
And?
2 carbons?
Yeah, it's attached to this carbon, it's attached to that carbon, and it's attached to a hydrogen.
Okay.
So it's got 2 carbons and a hydrogen. Which one of those wins?
2 carbons.
Yep, so this is high. And this is low. So my highs are on the same side. So this is a what alkene?
Z.
This is a Z alkene. Or you might call it a cis alkene. right?
Yeah, I think I can do the first one that you showed me where it's just like straight, but I think it starts getting challenging when it's like different.
You gotta be able to make a difference. So when your book tells you that when you can't make a determination on the first atom, you have to go out to the next set of atoms. And I always just keep track of it by arranging things in parentheses in order of decreasing priority. So I know carbon's a bit bigger than hydrogen, so I always start with the high priority stuff first. And then I just look until I find a difference. And ask myself which one wins. Make sense?
Yes, thank you.
I had another question. It was back in chapter 2. I think it was problem 29. And it gave you a bunch of molecules, had two portions that were highlighted. And it was asking, I forgot which one. It said which one is more acidic or more basic. But I would just confuse how I would figure that out from just looking at the molecule.
Yeah, this is one I did not assign. It's one you're looking at, right? So, and it's got this oxygen and this oxygen highlighted, right?
Yes.
And the question is what? Determine the more basic of the atoms. What does it mean to be a basic atom?
Like in terms of pH or like donating.
pH has something to do with it, but I like the second word you used. Donating. Donating what?
Pairs of electrons.
A pair of electrons, right? Which one of those atoms would be more likely to donate its pair of electrons is really what's being asked.
Oh,
Okay?
okay. Okay, that makes sense.
That's really what's being asked. And when you look at that, you go, well, golly, this oxygen has 2 lone pairs and that oxygen has 2 lone pairs. But which one's more likely to donate it? I'll figure that out, right? I can draw a resonance structure for this molecule, right? I can draw a resonance structure where I push this pair of electrons here and push this pair from the pi bond onto oxygen, and I end up getting this resonance structure. I cannot draw a resonance structure where I push these electrons down to carbon. Why is that?
To expand the octet rule.
Yeah, it would violate the octet rule. Nor can I move one of these electrons to this oxygen because that would also violate the octet rule. But what I've just done here does not violate the octet rule at all. Right? Everything still has an octet. We certainly have some charges on things now. Now, looking at that, which atom that's highlighted would you anticipate being more likely to donate a pair of electrons?
I would say the OH molecule is more likely to the oxygen molecule than the hydrogen.
Why?
Because, like I said, it could form the resonance structure without violating the octet rule. So
Okay.
it would be more stable that way.
Now, it donated its pair here to generate the resonance structure, you're right. But we're really talking about being able to donate its electron pair to something else outside of the molecule, right? So now think about that. If you're positively charged and you're an electronegative atom like oxygen, are you going to want to give up more electrons?
No.
Why not?
It's electronegative and wants to hold on to it.
Yeah, and it's already positively charged, right? So this pair of electrons are going to be held very tightly by oxygen. But now oxygen here has an excess of electrons. It has a negative charge formally. So it turns out that this is actually the more basic oxygen atom in that molecule.
Okay. That makes sense.
again, the thing about chemistry is they're all relative arguments. Right, and most students, even most professors, like to deal in absolutes.
Yeah, that's what makes it hard, because I never know what could happen.
Well, that's not true.
Well, there are rules, yeah.
Right, you've got rules, you know the basics, you're answering questions here. It's really just about building your confidence to be able to make that argument. This relative to that. And this applies to more than just chemistry. I mean, in my normal day job where I'm dealing with academic things as an associate provost, people want to make absolute arguments, but in fact, arguments are almost always relative. We can do this or we can do that, which is better, right? Or we can do these four things, which is better. It applies in life. You make these types of arguments every day. You shouldn't be afraid of making those arguments here, right? We know how these atoms can behave, and now, relatively speaking, I know that this atom would be more likely to donate its electron pair relative to that atom. Both could. They've got lone pairs, right? But we just made the argument that that oxygen atom with the hydrogen has a formal positive charge. Oxygen's already electronegative, so it's not going to be more positive. The one that's negative would be more likely to donate its electron pair. And so that's how we make those types of arguments. And that's going to just take, it's going to take time and experience for you to develop that comfort level. And the first exam will help develop that for you. What else?
I think, like, could you do some examples? And I could give you some from the book of just like naming that's like tricky, like complicated, like when the shapes, like if it's like isopropyl or like just like confusing things like that. Like I know the methyl and I know like the butyl or whatever, but I think I get a little tripped up on when it's like random shapes. It doesn't look like a line.
Let's try that. What's the first rule of naming any compound?
Finding the longest chain.
We got to find the longest continuous chain, right? So let's see if we can figure it out. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. It's starting to look like 8 might be it. Let's just make sure. 1, 2, 3, 4, 5, 6. 5, 6, 7. Yeah, 8 is going to be it, right? So I'm going to circle that. Everything in the circle is taken care of by what? The parent chain, right? That's the parent.
Okay.
What's the parent here? What is the parent? This is octane, right?
Oh, okay.
8 carbons.
Yeah.
Right? Now we got to figure out how to number it, right? But before we do that, let's name the substituents. What's this substituent? CH2CH3.
Ethyl.
Ethyl. And this is 3 carbons, so it's a propyl, but it's at the 2 position, so we call this isopropyl. And we got a number, right? We can number 1, 2, 3, 4, 5, 6, 7, 8. Or we can number 1, 2, 3, 4, 5, 6, 7, 8. Which way do we go?
From left to right.
Why did we go from left to right?
Because the lowest number
Right.
substituents.
Now I come to this substituent at carbon number 4, right? If I go this way, I get to this first substituent, also at carbon number 4. It's the same both ways. That first point of branching is going to be the same both ways, right? So I got to figure out. Now I've got an ethyl and an isopropyl. Which one is going to be first?
Is that when it goes by the
It
alphabet?
does.
Okay, so E's before I, so you would read from right to
Yeah.
left.
So this is going to be for ethyl, 5 isopropyl octane. Okay. And that just happened to be that way. Does that make sense? What else? Making sure nobody's texting this come up or anything.
I know we didn't really talk about it in class, but could you explain how strain works in terms of like Newman projections and staggering ellipse conformations?
Yeah, so we did talk a little bit about it, right? So we talked about the fact that if I have a molecule right, we all agree that a methyl group is bigger than a hydrogen? Okay. So I have these big methyl groups that are getting close to one another in that Newman projection. That is what we call torsional strain. Your book talked a little bit about that, right? And it's because things don't like to crowd each other and get in the same space. It's just like people. If I had a classroom full of people in here and I said, we're going to now occupy only half the space, you all would have to get closer together. Would you be more comfortable or less comfortable?
Less.
And then if I took that space and I halved it again, you would be even less comfortable. You'd eventually get to a point where you would be like, no, not at all, and you'd start pushing back, right? And that's what's happening here. These things are getting so close to one another that they start to repel each other, right? And so as the big groups get close to one another, right, we start to have this so-called torsional strain, and it's really the atoms pushing back on each other to get as far away as possible.
So it's more stable when they're farther apart.
Yep, the bigger group wants to be farther apart, right? So this is the example we did. And this group are as far apart as they could possibly be when they're 180 degrees to one another.
So in like an exam question, you would have, say like three different projections, the one on that left with like them on opposite ends would be, and it asks like which one is the most stable.
Yeah, I could ask all sorts of questions. I mean, maybe I could give you these two, or maybe I could give you a couple more to choose from, right? To where maybe it's so maybe you've got those three, and I ask you I could ask you which of those is the most stable. I could ask you which one of those is the least stable. You just identified the most stable. Which one would be the least?
The middle one.
This one, yeah. Because, actually I needed to draw that just a little closer to be correct. So ignore those pieces there. But yeah, those are eclipsing, right? And that eclipsing interaction would make that the least stable, and then this would be kind of in the middle. It would be in the middle range of stability. Of the three.
Okay, so also, what about whenever it is like CH3, parentheses, CH2, parentheses 3, and you have like, you know, you have to use like the parentheses because it's a lot. So the more carbons there are, the more stable it is. Like if you had a CH3, but then also like one with the parentheses, how would that affect it?
Something like that? Not exactly sure what the question is.
So like, it would still apply, like,
What is it?
like the I don't know what I'm trying to say, but like, it being stable, is it more likely to be stable when the more carbons are farther apart or closer?
We always want carbons to be as far apart as possible.
Okay.
But if I was giving you a question, let's say I gave you this formula, and I said something like, what would the Newman projection for this be looking down the carbon-3, carbon-4 bond? The first thing I would do is convert that to a bond line drawing, right, which is how many carbons total?
Okay.
8. So this is an octane, right? Right, so it's that. So this is that. And I want you to look down carbon-3, carbon-4. This is carbon-1, carbon-2, carbon-3, carbon-4, carbon-5, carbon-6, carbon-7, carbon-8. So I want you to look down this bond right here. Right? Carbon-3, carbon-4. So carbon-3 would be my front carbon, because I'm going to look down this bond. And carbon-4 would be my back carbon. Well, looking at this, if I picked that up, made a model of it, and turned it, what I would see is that I've got an ethyl group going up, right? Carbons 2 and carbons 1. 1, 2, and there's 3, right? There's also 2 hydrogens attached to this. Okay, so that's my front carbon right there. This is going to be my back carbon, the circle. Right, so what's going to be attached to that? 2 hydrogens, and then 5, 6, 7, 8. That's what that Newman projection would look like, looking down that carbon-3, carbon-4 bond. This group and this group, again, are as far apart as possible, so it's stable. I can look down a Newman projection here, here, here. I mean, any one of them, I can look down a Newman projection. It's always just looking down the 2 carbons at a time. Does that make sense? What else?
I just thought of one, but I forgot it's you guys.
Okay. So, example 3.5,
3 point what? Example 3.5?
yes, it's naming the cycloalkanes that look kind of complicated. Like when it goes to the 2-sec-butyl, like those types of things.
Yep.
I think,
So are you looking at like D?
yes.
Let's do that. So the thing that it first asked us to do is to come up with the formula, right? So 1, 2, 3, 4, 5, 6, 8, 9. I've got 10 total carbons. It's going to be C10, H. There's 3, 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that should be C10H20. Now we've got to number and name this. such that we get the right stuff. So this is going to be a cycloalkane, excuse me. What is the cycloalkane? What's the name?
So that's where I'm kind of confused because I know that the box kind of is like the main part of the.
It is. It's the cyclic part, right? I can start
Yes.
here and I can go all the way around and get back to the starting point without ever lifting my pencil.
But then I'm like,
That's the cyclic
what
part.
about the longest continuous chain?
In a cycloalkane, it's the cycloalkane
Okay.
piece. For the
Okay.
purposes of this class, there are some rules where you would name it as the longest chain, but we're not going to get into those.
Okay.
So how would we name the box?
If it's 4, it's butane.
That's right. What are these groups?
Methyl.
Okay, so we got 2 methyls, right? What's this group? How many carbons are in that group?
There's 4.
So it's a butyl group, but it's not a butyl group where it's just attached at the end. It's on the next carbon, right? So this is called sec butyl. Why is it called sec butyl? What kind of carbons? So if we think of it like this is the group, okay? And this is where it's attached. But don't assume that that's a carbon yet, right? Just think of it as a normal carbon, right, in butane. What kind of carbon is this?